Okay. In that case, there should now be a correct Tinkercad link posted to this circuit with the LEDs already wired, so we can kind of all start with the same hardware. Where we are going here, I'm actually going to pull up another mouse. There we go. Tab or canvas real quick. Milestone 2. So there's 2 initial milestones you have to do for the robot. One is kind of a short design pitch, 5-minute presentation to the TAs. That information and the rubric for it are on Canvas. The other one is just basic robot steering. Okay, so there is this diagram on Canvas, right? You need to go build a robot and wire it and program it such that it can drive forward, backward, and turn left and right. It's kind of your basic baseline the bare minimum you need to have to be able to do this competition, right? In order to do that, you're going to need 2 H-bridges and 2 motors, right? So you've already in the lab, you should already know how to use 1 H-bridge, so you're now basically doubling that, but you're going to need to write the code to steer. So that's kind of where we are headed today. But since Tinkercad doesn't have the exact same H-bridge as the one you have in lab, and I didn't want to deal with all the extra wiring, I want to focus on the code. We're just going to use LEDs to represent the motors. Okay, so same digital output pins that you would use to control an H-bridge, but say green LED represents forward, red LED represents backward for each motor. Okay, so by seeing which LEDs are on, we can just pretend that the robot would either be driving forward, and there's no rack and pinion steering here, right? It's just 2 wheels. So if both wheels spin forward, the robot drives forward. 1 wheel spins backward, and the other wheel spins forward, the robot turns. Okay, that's all there is to it. So, as a little bit of practice to make sure you remember how to do the stuff we did before break, or if you don't remember, you can refresh yourself. Starting out, I want you to just set those 4 pins as outputs. Okay, we have Arduino pins 8 through 11, all connected to the LEDs. We have the code skeleton for the main function and the while loop. There is supporting documentation on Canvas if you need it. You have the ATmega 328P datasheet. You have the Arduino pinout diagram. Should be able to do it in 1 line of code. Set those 4 pins as outputs. Okay, a common symptom of not doing this properly is your motor spinning really slowly. Okay, if you put your robot down and you notice, hey, one motor is spinning way slower than the other. It's not that it's not working at all, but it's not spinning anywhere near as fast as it should. That is probably because one of your H-bridge pins is not set as an output, it's still set as an input. Okay, the symptom you'll see with that with LEDs is an LED being way dimmer than it should be. It's still on. It's not like it's totally off or not working, but your LED is just mysteriously dim. It's probably because one of these pins is still set as an input. So, very simple. One of the first things we did when we were learning to do registers, but you need to make sure you still know how to do it right. Okay? Here for a minute. Okay, as a reminder, pull up the pinout diagram, look at the pins you're using. We're using pins 8, 9, 10, and 11. So that's port B, bits 0 through 3, PB0, PB1, PB2, and PB3. Okay, so I want to keep moving kind of quick here so we can get to the more interesting part. So that's just going to be a single line of code, DDR-B, my data direction B register, using either bit shifting or just writing the whole thing out. 1, 2, 3, 4. 4 zeros, 1, 2, 3, 4, 4 ones, semicolon. Okay, that's setting these 4 pins as outputs. Great. Questions? Anybody not remember how to do that? Confused about that from before break? And again, don't hesitate if you're lost now, because I don't want you to just be lost for the next 40 minutes. Okay. Next, I want you to write code to drive forward, meaning green LEDs on, red LEDs off. Okay, so we're not actually wiring the motor, we're just using the LEDs to represent that. So you want the both green LEDs on, representing each motor spinning forward. And I want you to make sure you use masking. So in this circuit, we only have these 4 LEDs connected. There's nothing else. In your robot, you're going to have a bunch of other stuff connected, possibly on port B. Okay, you've got your color sensor. You're going to have 2 line sensors probably. You're potentially going to have additional motors. Okay, so if you have something else plugged into pin 12, you need to make sure whatever code you write to control these things does not affect pin 12. Okay, and you might say, oh, well, I would just put everything else on port D and leave nothing on port B so I wouldn't have to worry about it. You're going to need to use a lot of pins. Again, there's a lot of stuff connected here, so you also, when you go build your robot, might not choose to stick with these 4 pins for the H-bridge. There's nothing saying that these are the correct or right 4 pins you have to use. This is just what I picked for the sake of this demo. Okay, so if you decide to move some or all of your H-bridge pins down to port D, and you have other stuff plugged into port D, then you would need to use masking there as well. Okay, so I don't hear a lot of typing, so that was either really easy or everybody is just waiting for me to do it because you don't feel like thinking about it yourselves. Which one is it? Easy? Okay, maybe that's a good sign. Okay, so again, if I wanted to do this the lazy way, it'd just be port B, if I can spell. Okay, I could just do this, right? 1, 2, 3, 4, 1, 0, 1, 0, or I could use bit shifting, however I want to do it. But again, the problem with that, so that's doing what I asked you to do, right? Turn the green LEDs on and the red LEDs off, but that is overwriting all the other bits with all the other pins with zeros, which is going to be bad if I have other stuff connected to those pins, and this is all I want to do. Okay, I don't want to mess up my color sensor reading. If I have some third motor connected doing some other thing, I don't want to affect those, right? So I want, do this properly with masking, which everybody has figured out by now, or we need more time? You good? Okay, I see thumbs up. Okay, so I'm going to do that with masking instead. So, for example, if I want to make sure I turn the green LEDs on, I do this, right? That turns the green LEDs on using the bitwise OR operator. But I also need to make sure I turn the red LEDs off, right? If the red LEDs were on from something previously, this line of code is not going to turn them off. I need a bitwise AND operator to do that. So port B and equals 0B, 1, 1, 1, 1, 0 to make sure, sorry, 1, 0, 1, 0. Remember the AND 1 here is leaving it unchanged, so I'm not affecting these first 4 bits, I'm not affecting the green LEDs with this line, but I am turning the red LEDs off with that bitwise AND 0. Okay, so don't forget, I think it's easier to think about turning things on with the OR operator than turning things off with the AND operator, but you need to do both here. Okay, remember, you don't want to, if you don't have that second line and your red LED, say we're going to get to this in a minute, but say the robot had been driving in reverse before this, so the red LEDs were on, right? And I only have this line, then I'm going to turn the green LEDs on too. Both inputs to the H-bridge will be high and the motor will stop. It's not going to drive forward. Okay, so when you want to switch directions or turn, you have to make sure, if you want your motor to be spinning, you always want one input high and one input low. Okay, Especially if both are high or both are low, the motor's going to stop. Okay? Okay, now, same thing. We're going to add a short delay. Say delay underscore ms 1000 for 1 second. Do the reverse. Write code to make the robot go in reverse. We're going to drive backward. Okay. Green LEDs off, red LEDs on. Okay, fill that in. Then add another delay. Okay, and then once you run that, it should just kind of be a blinker, right? It'll blink the green LEDs on and then the red LEDs on. Again, if you're stuck, ask somebody near you for help or ask me for help. I don't want you to just be lost for 30 minutes. Hint. Probably going to want 2 more writes to the port B register. Again, now you're turning the green LEDs off and the red LEDs on. I'll do 1 more lap, then come back and fill it in. Anybody got the LEDs blinking? Okay. I don't see a lot of blink here. I don't see a lot of successfully blinking red and green LEDs. Like I've seen some green ones turn on. Okay, I see some red and green blinking back and forth. Anyone stuck? What's up?
Why do we need to have line 9 for the and equals?
That is turning the red ones off. So this is going to matter when we do a loop and we're alternating. If initially, everything is off initially, right? So if the very first thing I want to do is just turn the green ones on, then I would only need this line. But say your previous state is unknown, you could have been driving in reverse, meaning the red ones were on. Then you need to make sure to drive forward, you turn the red ones off. Okay, I'll demonstrate that in a second as we fill this in. So, I'm going to drive backward. I want to turn the green ones off this time. So that's going to be a bitwise and for the greens. Okay, 0B, 1, 1, 2, sorry, 1, 2, 3, 4. And make sure this is up. 0, 1, 0, 1. So that is turning, these 2 zeros are turning the greens off. And then turn the reds on. Bitwise OR. 0B, 1, 2, 3, 4. 0, 1, 0, 1. That is turning the reds on. So if I run this, as long as I didn't screw that up, Okay, it's just blinking them. So green on represents driving forward, red on represents driving backward. Again, in your robot, these are going to be wired to your 2 different H-bridge inputs. We just didn't bother wiring the H-bridge here. So why do we need this line? If I comment that out, look at this is what this is going to do. It's going to turn the greens on, but then it's never going to turn the reds off. So the reds are just going to stay on the whole time, right? I drive forward, I call my drive backward function, so I turned the reds on, but then the next time I have my drive forward function, it's only turning the greens on and it's not turning the reds off again. So this would be drive backward, stop, drive backward, stop, instead of alternating between driving backward and forward. Does that make sense? Okay? All right. So we have code to drive backward and drive forward, right? That is not exactly, I don't remember which end of the screen my mouse goes off. It's my mouse there. There we go. Okay, I'm not going to bother pulling the diagram up again, but you have the basic idea here, right? We have code to drive backward, drive forward, drive backward. We can use delays in between to drive for a certain amount of time. So we do not have any sensor measuring distance. We're not using a wheel encoder to measure the RPM or number of revolutions of the wheel, but you can roughly open loop time this just by putting your robot down. You read the milestone instructions and it gives you, oh, your robot has to drive forward a foot or whatever it is. The TAs are not going to break out a tape measure and say you only drove 11 inches. That doesn't count, right? You can reasonably kind of ballpark it for how far your robot drives and how far your robot turns in a certain amount of time. So we're not going to do this yet. You could also write this for turning left and turning right. Right? So your robot's going to need to turn, not just drive forward and back. So that would be one green LED on and the other red LED on. But writing this big long string of port register writes, right? Just adding more and more of these for driving forward and copying and pasting when you need to do something more than once is going to start to get kind of cumbersome, right? You're just going to have this giant long list of register writes. And hopefully you learned in your whatever intro programming class you took that if you find yourself copying and pasting and reusing sections of code, it's probably a good idea to just put that code in a function that you can call more than once, right? This is not a new concept, right? Okay, good. So if you guys haven't heard about functions before, then I'm in trouble. So what we are going to do, or you don't have to do, but I strongly recommend doing, is putting this code in different functions, like a function called drive forward or turn right, whatever. You can call them whatever you want. You don't have to call them what I do. But that is going to make your life then much easier, both for accomplishing this initial milestone where all you're doing is steering, and later on when you're starting to make your robot react to sensors. Okay, so my left line sensor detects the line, so I need to turn right, or my ultrasonic sensor detects the other robot in front of me, so I want to go in reverse. Whatever that algorithm is, then you have these functions and you can just call them to make the robot maneuver. Okay? So the way we are going to do that, down here below our main function, int, whatever you want to call your function, right? So I could do drive forward. Okay? This function, if it does not have an argument, you can just leave these parentheses blank, or I believe put void in there. I don't actually know if it makes a difference. I think it'll still run the same way. We'll find that in a minute if this compiles. I might have that wrong. So if you just want a function that doesn't return it, doesn't require any arguments or inputs, and doesn't really return anything, then this is all you need. Int, name of the function, open close parentheses, curly brackets, and then you just put whatever code you want in here. Okay, so I could copy my drive forward registers, paste them in here. Probably a good idea to leave a comment trail as you go so you don't lose track of what all this does. So for example, this one sets pins 9 and 11 high, and this one sets pins 8 and 10 low. And then if I want to call that function, I just write the name of the function up here like that, again with the blank parentheses. And again, I forgot to jot down in my notes whether I need that void there or not, so let's see if that runs. Okay. So it's doing the exact same thing, right? The only difference is that now it is calling the drive forward function from here, jumping down and doing the stuff in this function, and then jumping back to where it left the loop. And so now if I need to call drive forward again later, which you're going to need to do a bunch of times as it drives around in that not quite square shape, all I have to do is copy this line rather than having these registers repeated every time. Okay? Now, with this setup, I still have the delay separate from the function, right? So all this function is doing is toggling the register bits, but there's no delay in the function. So if I wanted to, I could put a delay inside this function as well. For example, now I'm going to give this function an argument. I'm going to say int t, so this function is going to take an integer variable as an argument, and then I can do delay mst. So now the delay is inside that function in milliseconds. So if I call the function now, I can give it an argument like this, 1000. So that's saying drive forward for 1 second. Right? So either way works. And again, for milestone 1, maybe this kind of makes sense because it keeps your code a little cleaner and you don't need these separate delay commands after every action. Depending on your robot's algorithm and what you're doing with interrupts and things, you might not want delays inside those functions, right? You might want to just change it so the state is driving forward, and we'll talk more about something called a finite state machine later in the semester. Change it so your state is driving forward, but then you're kind of waiting to react to a sensor input to change your direction, as opposed to saying, oh, I'm just going to drive forward for 2 seconds no matter what. Okay, so again, if I run this, as long as I didn't screw up, should now do the same thing. Okay, it's calling my drive forward function for 1000 milliseconds, drive forward 4000 milliseconds, and then jump back up here and do the drive back part. Okay, I went through that a little fast. Questions on moving that code into a function? Yes?
Can the function be both below and above, or just have to be below?
Good question. I think by convention I have always sort of put them below, but if we do that, so I know, but by convention I've always kind of put the interrupt service routines up here above the main function and then other functions below. You can also, for bigger, more complicated programs, actually split things out into separate .h files and then include whatever file name .h up here that'll include it. The programs we're doing in this class usually don't get so big and complicated that you need to do that. You can just kind of fit it all in one single .ino file. With the caveat that this compiled fine in Tinkercad, you would need to double check on a physical Arduino just to see if there's anything different with the compiler. So again, I am not a computer scientist by training, so I don't know if one of those is considered more proper than the other. But as far as I know, in this case, either one works. Okay? Okay. We did that for one function. What I want you to do with the remaining time is do it for the other 3. Okay, so we already have this set up for drive forward. I want you to move drive backward into a function and then also write functions for turning left and turning right. Okay, and this is going to basically lay the groundwork for what you need to do in milestone 1. Okay, so ideally, everybody in your group should have code that works to do this with the LEDs. Okay, maybe, and this is where we're going to kind of branch off and allow different styles, right? If you prefer bit shifting over how I did this, or you don't like having the delay in the function, you like having the delays up here, do whatever makes the most sense to you, right? That there's more than one way to do this that will work equivalently, and then as a group, you're probably going to want to standardize, right? If all 3 of you wrote it in different ways, and you don't want to wind up having kind of patchwork of code where people have very different styles, you might want to choose, okay, we're going to use this person's code or do it this way. Again, also with the caveat that you might be changing these pins in the future. Okay, I just picked these four here because I think it's kind of convenient to have all of your H-bridge pins on the same port as opposed to having 2 on port D and 2 on port B and then needing even more port register rights over here. But once you happen to function, maybe not that big of a deal. Okay, so we are going to, on Wednesday, start talking about, you guys can kind of work as I babble here. Something you will notice as you build your robots, and may have already noticed when you did Lab 3, the motors are kind of janky and the robots don't drive straight all the time. Okay, if you just put one down and turn both motors on full speed, they will tend to sort of veer off gently in one direction. So one way to account for that is basically slowing down one motor, right? So if I'm turning left too fast, if I slow down my right motor, then you can calibrate to make your robot drive straighter. We are going to learn how to do that using pulse width modulation, which we have talked about briefly earlier in this semester. So the Arduino pins with these little squiggly lines next to them are capable of generating what's called a PWM, or pulse width modulation signal, which is rapidly toggling the pin on and off. So remember, these are digital pins. They cannot output a true analog voltage. They can't output 2.5 volts. So if you want to control the speed of your motor, what you do is you turn it on and off really, really fast. Okay, so if it's on half the time and off half the time, and you're switching that fast enough, then the motor will roughly move half speed. So this is what you did, I think, with just the function generator in Lab 3. Now we're going to learn how to do it with the Arduino pins. Okay, so that is, where things are really going to start to diverge and branch in terms of what you can do with your robot. I want you to know how to do that, but doing it is not mandatory. Okay, if you want to just be to hell with it, we're driving full speed all the time and we drift to the left a little bit, fine. Okay, if you say no, we really want to calibrate so we can drive straight, or we want to, some part of our algorithm or strategy is going to involve not driving full speed all the time. For example, if we're on a border, we want to decrease our risk of driving off the edge, so we're going to drive a little slower if we're on the border or something like that. No right or wrong solution there. But that is where we are headed Wednesday, introducing PWM, where again, only the pins with squiggly lines can do PWM. So depending on your decision about whether you want to control motor speed and whether you want to control it in forward and reverse or just one. So maybe you only care about going forward at half speed, but you don't care about going reverse at half speed. You might need to move these wires around to be on the PWM pins. We are also, depending on how far we get Wednesday, then on Friday, going to learn about servo motors. So the motors you used in lab are kind of modified servo motors that behave like DC motors. They just have 2 wires. The direction of current through those wires determines the motor direction. The duty cycle of the PWM signal through the high wire determines the motor speed. Servo motors, which I can actually kind of zoom out and give a preview here. The ones in your lab kits have 3 wires. So there's a power wire, a ground wire, and a signal wire. So a positional servo motor takes a control signal that determines its angle. So these things have a range of roughly 0 to 180 degrees for the positional ones. So if you want to build some mechanism, so a lot of in the past, students have built robots with arms that deploy or something that kind of scoops or gathers cubes or whatever it is. Again, this is optional, don't have to, but we are going to learn how to control those also using a PWM signal. So that's kind of where we're headed this week with what you can use all of these different pins for in terms of motor control. The following week, you already know how to use the color sensor from Lab 4. We are going to learn how to use line sensors to detect that black border and ultrasonic sensors if you want to detect the other robot. And so that is where we're kind of going this week and next week. But again, this is going, I want to emphasize that this is going to diverge, right? Like I will be doing example code in class for a lot of these things. Which pins you pick and even which parts you use for the project is going to be up to your group. Okay, many of you have to do this, right? To pass milestone 1, your robot has to be able to steer. Pretty much all of the other additional motors and sensors are going to be optional and depend on your robot's design. as usual, you guys are suspiciously quiet. Can't tell if that means there's no questions or everyone's bored or what. Nothing? Sure.
Just want to clarify, if you put like all the drive code main functions and you don't have like a clear order of calling them, is it a better idea to clear all pins to 0 before you write them to the English functions?
So if you better idea to clear all bits to 0 before, what was that last part?
So the clearing now is targeted specifically to 2 pins, but in the real thing you expect to call these in a series, like certain orders, right? So do you want to clear all the pins before you?
No, you don't want, so you want to use masking to only clear the pins corresponding to your H-bridge, right? So if you have your color sensor or something plugged into one of these other pins, you want to make sure it is not affected by either one of these writes. You should be able to assume that the state before you call any of these functions is unknown both on your H-bridge pins and on the other pins. Right? So if these are all, if kind of before I call this, right, say this is 0B, question, 8 question marks, right? And I don't know what any of those are, but I know which ones I want to change. I know I want to set this one high, and I know I want to set that one low. And then same for, I know I want to set this one low, I know I want to set this one high. I don't know what these are, but I don't care, I just don't want to change them. Does that answer your question?
Yeah.
Okay. I mean, I guess arguably, in your main function, you could always kind of initialize everything low, but those registers all default to all zeros anyway. So when the robot first boots up, it's not going to drive anywhere unless you tell it to, because you need to set those pins as outputs with DDR. But even as you set them as outputs, then the port register is going to default to all zeros. So the default action is the robot will just sit there when you power it on until you write something high in a port register. Yes?
What's the difference between like a 130 steering motor versus like a 180 drive motor versus like the motor that we
So a 130 steering motor, that I don't know what that is. Is that what you said?
It's like some other motor that you put in like all the RC parts.
Okay. There are more motors than we have time to cover in this class. The very short, so I'm not familiar with there are different types of positional servos that have different angular ranges. The 180 is kind of a ballpark, so that 130 might just be a positional servo that only has a range of 130 degrees instead of 180 degrees. I'd have to see like a data sheet to see the motor to be sure. Some of them are only more like 160. It doesn't actually get the full 180. But these, let me pull it out again. These little blue ones in your kits, these have an internal feedback mechanism. So they actually have a potentiometer inside that is measuring the angle. So if you send it a control signal or a command to rotate to 45 degrees, it will do its best to maintain that 45 degree position. If you load it and tip it to 90 degrees, it'll go back. Versus the DC motors that just have 2 wires, these do not have any built-in feedback mechanism. So you would have to add a separate external, what's called a motor encoder, that can measure the RPM, either the RPM or the angular position. So if you look at these servos, have these little kind of blue translucent plastic cases. You can kind of look in from the side and see there's a little circuit board inside. So they have kind of extra built-in control circuitry. There are also, I've been talking about positional servos so far. There are also continuous rotation servos that can rotate a full 360 degrees, but they also have internal control circuitry to measure the speed, not the angle. So you can't control the angle directly, but you can control speed either in the clockwise or counterclockwise direction. Then there are stepper motors, which we don't have time to get to in this class, that can do both, can rotate a full 360 and you can control the precise angle. So we could fill like half the semester just on different motor types. These are brushed DC motors, which are cheaper. We don't have time to talk about brushless DC motors, which are what you'll usually find on drones because they're more efficient. So kind of a long tangent. But if you have questions about specific motors, Dave Martino in Lab is a good one to ask, or if you have like a data sheet you can post on Ed or something, I can try and explain the difference more. Okay, did I see a hand over here?
Yeah. So for the positional servos, are we able to disassemble the case and then add the wire that would connect to the output potentiometer so that we can measure the rotation of the servo directly instead of assuming that the servo has made it to its correct position? Or would that not be allowed for?
I am gonna lean, well, for the servo, so the question was basically, can you modify the servo and drill open the case? For the ones in the lab kits that are kind of part of the base kit that need to be reused year to year, no. For ones that you buy with your team's budget, yes. Okay, so if basically the people buy different parts that, since they're not standardized from team to team, they don't necessarily need to be reused the next year. You are more free to do whatever you want with those. Although I'd say for the, I guess depending on the, these little plastic ones can't handle much of a load, and it's generally advised not to back drive them too much, especially for the ones with plastic gears, because the gears will just strip. So if you are, and for the little 1-inch wooden cubes, that probably isn't too much of an issue, but if you're risking, maybe colliding with the other robot and the servo is really being back driven, and you can't actually assume the angle is safe, then yeah, maybe you would want to do that. Good? Okay. All right. How are we doing on the left and right function part of this? Stock questions. So you should be able to, once you run that, have the LEDs blinking in whatever sequence you call your functions in, but then you can easily rearrange the functions and change the times to call them for different amounts of time, right? And then that's what you're going to be doing for the milestone, is kind of fine-tuning those times to get it to drive in the required shape. Okay, so I'm not going to pull up the code. Hold on. Let's kind of just show you what it should look like once you've gotten it working. Okay. So here I have drive forward, drive backward, turn left, turn right. So you see now it's alternating between those 4 states. And again, I have this isn't actually doing what you would need in milestone 1. This is just demonstrating the 4 functions for 1 second each. But once you have, and I'll post the Tinkercad circuit link to this after class, but now, see, this is just much more compact, right? Like all the messy stuff with the registers is down here in my drive forward and drive backward functions. And I can just call these functions whenever I need them to control the robot. Okay, so that is kind of what you're, I am recommending this because I think it is easier, but technically you don't have to do that, right? You could complete the milestone just by having a giant list of all of these individual port register writes. I think that's really messy and probably not a great idea, but we're not grading you on the way you write your code, with the caveat that you can't use Arduino libraries, okay, right? So no digital write or anything here. But as long as your robot can perform the task, it doesn't matter how you wrote it. Again, and then there's also the ChatGPT caveat there, right? Like some people have gotten working ChatGPT code out of the various assignments, many have not. So if you just try to ask it to do this, my hunch is that it's going to be more work to search through and find the one place it got a bitwise operator wrong or something and fix it yourself than it would have been to just do it yourself to begin with. So again, that's my experience so far and what I would recommend. This kind of basic I/O register stuff you should be able to handle at this point and get this working. Questions? Okay, again, I don't have the timing of this all perfect yet, obviously. We still have like 4 minutes left, so I'd say I will stick around if you do have questions as you're trying to get this to work and you want to stay until 12:05. If you're done and ready to head out, that's fine too. Okay? Thank you.